In this example, we're going to determine the rate equation for the reaction listed above, given some experimental data. The data are as follows. We have 3 trials. In those trials, we varied the concentrations of the reactants. Remember, the rate depends on the concentrations of the reactants. The product's concentrations don't have anything to do with it. So we vary the concentration of the reactants, and we measure the instantaneous reaction rate. From that, we can determine the rate equation. Look at the general form of the rate equation. Rate equals K times the concentration of one reactant raised to some power times the concentration of the other reactant raised to some power. The point of this data is to let us figure out K, X, and Y. How do we do that? Well, we have to isolate our unknowns. We have 3 unknown things in this equation. We don't know K, we don't know X, we don't know Y. We want to try and isolate them. Is there any way we can use these trials to isolate these unknowns? And the answer is yes. Look at trials 1 and 2. In those 2 trials, the concentration of ICl did not change. So any difference in rate between those 2 trials can't be due to the concentration of ICl, because ICl doesn't change in the trials. It also can't be due to K, because K is a constant. It doesn't change either. So between trials 1 and 2, the only thing that changed was the concentration of H2. So any change that occurred in reaction rate has to be as the result of the change in concentration of H2. Well, how did the rate change between trials 1 and 2? Let's divide the second rate by the first rate. If we do that, we find out that rate 2 over rate 1 is 2. That means the rate doubled from trial 1 to trial 2. Now that's solely because of H2. So think about it. We doubled the concentration of H2. That's like putting a 2 in for the concentration of H2. Well, if I put a 2 in for the concentration of H2 and raise it to the Y power, according to my data, I need to get a 2. Because after all, the rate doubled. So the rate went up by a factor of 2. The only thing that changed was the concentration of H2 went up by a factor of 2. So the only question I have to determine is, what number fits into Y? So that when I raise 2 to the Y power, I get 2. I take the change in concentration, 2. I raise it to my power, Y. And that has to equal the change in rate, 2. So what does Y have to be? Y has to be 1. 2 raised to the 1 power is 2. So we use these 2 trials to figure out what Y is. Now let's see if we can do the same thing to figure out what X is. We need to find 2 trials in which the concentration of H2 did not change. That way we get rid of any influences by H2. That's true in trials 2 and 3. In trials 2 and 3, the concentration of H2 was constant. The concentration of ICl varied. It went up by a factor of 2. So once again, I can use these 2 trials to isolate just ICl. Any change that occurred in reaction rate has to be due solely to ICl. All right, well, once again, we divide the second rate by the first rate. 0.0408 divided by 0.0204 is equal to 2. So between trials 2 and 3, the rate doubled again. Now remember what we do. We take our change in concentration, 2. We raise it to the power, X. And that has to equal the change in rate, 2. So what does X have to be? X has to be 1. All right, so now we know a lot more about the rate equation. We know that rate equals K times the concentration of ICl raised to the first power times the concentration of H2 raised to the first power. Now before we go on, notice that this shows we can't use the stoichiometric coefficients to determine X and Y. The stoichiometric coefficient in front of ICl is 2. But in the rate equation, we only raise ICl to the first power. So X and Y have nothing to do with the stoichiometric coefficients, so we can't use those. We have to look at the data. Okay. Now it turns out we have everything we need to know to solve for K now. Because look at the trials data. We have concentrations and rates for several different trials. If I take any one of those trials and plug in the rate and the concentrations, the only unknown in the rate equation will be K. So, let's take the first trial. The instantaneous rate was 0.0102 molars per second. We make that equal to K, which we don't know, times the concentration of ICl, 0.25 molar, raised to the first power, times the concentration of H2, 0.25 molar, raised to the first power. Now we can use algebra to solve for K. K is 0.16, and what's the unit? Well, I've got molars per second, and I'm going to divide by 0.25 molars, and then 0.25 molars again. So the resulting unit is 1 over molar second. So in the end, I know the rate equation. The rate equation is K, 0.16, 1 over molar second, times the concentration of ICl raised to the first power, times the concentration of H2. If you're having trouble doing these kinds of problems, just remember what we did here. We looked for two trials in which the concentration of one reactant didn't change, and the concentration of the other reactant did. We find how the reactant changed in concentration. Did it double? Did it triple? Whatever. Then we look at the rate and see how it changed. Did it double? Did it triple? Whatever. Then we take the change in concentration, double, triple, quadruple, raise it to the power, X or Y, and set that equal to how the reaction rate changed. Did it double, triple, quadruple, whatever. That will allow you to determine the power, X or Y.